Today we'll cover section 12.6 on expectation. Suppose I ask you to play a game with me. Here's the deal. You roll a standard die. If you roll an even number, you will win $30 times the number that you roll on that die. If you roll an odd number, you'll lose $30 times the number that you roll. Or if you want to, you can reverse it so you'll win with the odd rolls and lose with the even rolls. Which one of those would you choose and why? The concept of expectation, or sometimes it's called expected value, provides a formal way of deciding issues like that. So this is the topic we're talking about today, and we're going to illustrate this idea of expectation through basically setting up games and also some real-life situations where it might come into play. Let's go back to the die roll problem, though. I want to build a chart that tells us about winning and losing based on what the die roll is. And we want to use that as a basis of deciding whether to choose the odd scenario or the even scenario. Let's go right now, though, with the scenario that I first posited, which is that you win $30 times the number that you roll if it's even, and you lose $30 times the number you roll that it's odd. If we do that, suppose you roll a 1. Well, 1 is odd, so you'd lose 1 times $30. You would lose $30. I'm going to indicate that by putting a negative sign in front of it. If you roll a 2, that's an even number. You'll win 30 times 2. You'll win $60. If you roll a 3, that's odd, so you lose 30 times 3, which is $90. You see how this is working. If you roll a 4, that's even. You'll win 30 times 4 equals $120. If you roll a 5, that's odd, so you lose 30 times 5, which is $150. If you roll a 6, that's even. You win 30 times 6, $180. In addition to how much you can win or lose, you've got to look at the probability of each of those. If you win on something that rarely happens, that's different than winning on something that happens a lot, and vice versa with losses. So the probabilities are important here. Now with a die roll, if the die is fair, it's actually going to be the same every time for this particular case. There's a 1/6 chance of getting a 1, a 2, a 3, a 4, a 5, or a 6. So in this particular problem, the probabilities are the same all the way down. But that, in general, does not have to be true. In this case, it is. So the probability of rolling a 1 is 1/6. The probability of rolling a 2 is 1/6. The probability of rolling a 3 is 1/6. The 4 is 1/6. The 5 is 1/6. And a 6 is 1/6. Now I want to do something to merge those two things together. And I'm going to do that by taking the first column, which are the values either won or lost, the dollar values, and multiplying each by their probabilities of occurring. So across that, I will multiply the first column number times the second column number, which is a dollar either gain or loss times the probability. So negative 30 times 1/6 is $5, and it's a loss, so it's negative $5. 60 times 1/6 is $10. That's positive, so it's a positive $10. Negative 90 times 1/6 is $15, but it's negative. $120 times 1/6 is $20. Negative 150 times 1/6 is negative $25. And finally, 180 times 1/6 is $30. So I've multiplied across, and what I've done by doing that is created a third column which merges the amount won or lost with the probabilities associated with each of those things occurring. It's kind of a blend of those two things. Are you with me? Multiplying the value from the first column, which in this case is a dollar amount, either won or lost, with its probability of occurring. And that's the value in the third column. Now I want to make this into one number which sort of encapsulates the whole thing, and I'm going to do that by adding up all those numbers in the last column. Now, you'll notice in this case, if I get a positive sum, that's good for me because that means I overall tend to win in this game. If I get a negative sum, that's bad for me if I pick the even ones, because that would be a loss for me on average. So anyway, I add up those last column numbers, and if you add up all 6 of those numbers, you get $15, and it's positive. So that means those even numbers were the best choice. It gives me, on average, a $15 win each time I play that game. Now, it doesn't mean I'll win $15 every time I do it, but if I play it a lot of times, I'll average in general winning about $15 each time I play that game. So definitely the evens are the best choice here. That number at the end, which is the sum of those products, is called the expectation of the game. And I've already alluded to this, but what that number means is if you play this game over and over again, in the long run, you can expect on average to win about $15 per game. If the expected value or the expectation had come out to be negative, that would mean on average you would lose money, so that would be a bad choice. Had that come out negative, you'd been better off flipping your choice and choosing the odds. Let's look at some more examples. In the simplest case, for example here, it says the outcomes of an experiment and the probability of each outcome are given in the table below. Compute the expectation for this experiment. They give you a column of outcomes, 5, 6, 7, 8, 9, 10, and the probability of each outcome. In any case, if they give you a problem like this, all you have to do is add a column for the product. Remember, we have a column for the outcome. In the previous example, it was dollar amounts. And then you have a probability column, and all you need to do is multiply across and then add down. So in this particular case, the expectation is 6.23. A problem like this is strictly giving you practice doing the calculations. I alluded to it earlier, but we did a lot of these things where you're just playing gambling games. But there are some actual business applications of expectations. In fact, there are tons of real-life applications of expectation, but we're going to talk about one in particular. This problem says when an insurance company sells a life insurance policy, the premium, which is the cost of buying the policy, is based largely on the probability that the insured person will outlive the term of the policy. Such probabilities are found in mortality tables, which give the probability that a person of a certain age will live one more year. But what the insurance company wants to know is the expectation on a policy that it's going to sell, that is, how much it will have to pay out on average for every policy it writes. That's an extremely important thing for that company to know. Let's look at a couple of examples. According to mortality tables in the National Vital Statistics Report, the probability that a 21-year-old will die within a year is about 0.000962. If the premium for a 1-year, $25,000 life insurance policy for a 21-year-old is $32, what is the insurance company's expectation for the policy? You've got to start out thinking just like you did with the roulette problems and all the others. You're going to build a table. So what we're looking at in that table basically is whether that 21-year-old person dies or not. So you could say let S sub 1 be the event that the person dies within a year. That's the term of the policy. And S sub 2 is the event that the person doesn't die. In other words, however you phrase it, you're looking at whether the person will die within a year or not. If the person dies within a year, the insurance company has to pay out the policy. If the person doesn't die within a year, then the company gets to make a profit on that person because that person had to pay for that policy. The probability that the person dies within a year is 0.000962. But if it does happen, the company has to pay out $25,000 to whoever the policy beneficiary is. However, keep in mind that the policy wasn't given free. The company charged $32 for the policy, so even if they pay out, they actually don't lose $25,000. They lose $25,000 minus the $32 that the policyholder paid to get the policy. So $25,000 minus 32 is $24,968. So it's close to $25,000, but it's not quite $25,000. So you have to adjust for that. The probability that the person does not die within a year is 1 minus the probability that that person does die. So if you take 1 minus 0.000962, you get 0.999038. Now, if that happens, the company keeps that entire premium of $32, and that's the company's profit for issuing that policy. And that's, of course, what the company hopes will happen. And I'm pretty sure it's what the person that took out the policy hopes will happen as well. In any case, you have to build a table. One row is the 21-year-old person dies within a year. The second row is that that person does not die within a year. The first column gives you the amount of profit, and we're looking at it from the company's point of view. And then the second column is the probability of that happening. So we'll start off just the same as we did for the roulette wheel problems. We look and see that the amount of profit that the company makes if that person does die within a year is actually a loss. So it's a negative $24,968. It's the $25,000 policy adjusted for the fact that they actually charged $32 for the policy. That's what the company will end up losing if that 21-year-old person dies within a year. However, the probability of that is very small. It's only 0.000962. So it's highly unlikely that that 21-year-old will die. Not impossible, obviously. And what happens if the person doesn't die within a year? The company keeps that $32 premium, so that's a $32 profit for the company, and that's highly likely. We already calculated that is going to be 1 minus 0.000962. It comes out to be 0.999038. So it's highly unlikely that the company will pay out that big amount, and it's highly likely that the company will keep the small amount, but not 100%. Now all you have to do is multiply across, taking more than 2 decimal places and rounding at the end, and then adding down that last column, and you'll find out that the expectation is $7.95, and it's positive. The company needs a positive expectation. If that number comes out negative, on average, the company is going to lose money on every policy, and a company that loses money on every policy on average is not going to stay in business. So on average, that company issuing that particular type of policy will tend to average $7.95 per policy issued.